Hey there! Welcome back to the Nauctis on YouTube. Man has created various modes of transportation for long-distance travel, even extending into outer space. To venture into space, humans began developing sophisticated space rockets. Rockets initially emerged in the 13th century in China for military purposes and recreational activities. However, their use as the primary means of transporting humans into space only occurred in the 20th century, coinciding with advancements in interplanetary science and significant technological progress. The rocket manufacturing process requires specialized factories equipped with adequate facilities and equipment, along with skilled and professional workers. One renowned rocket assembly factory is the United Launch Alliance, ULA, located in Decatur, Alabama, United States. Spanning 1.6 million square feet, this facility has produced various rocket types, including Atlas V, 𝗤𝗂𝗃𝗲𝗃, and Vulcan Centaur. In the rocket manufacturing process, a 17mm thick aluminum plate stock is needed. One of the 4 double gantry milling machines grinds the aluminum into tanks and component patterns from the plate stock. This method reduces panel weight by 70%, while maintaining 75% material strength by cutting 70% of its aluminum. To provide strength, the cut aluminum sheets are shaped into square grids before proceeding to the next step. These cut aluminum sheets are collected to form stock panels, and to prevent aluminum oxide, they are immediately sprayed with a special liquid. The next stage involves bump pressing, a procedure to shape curves on the panel, forming the side panels of the booster. Aluminum components like the panels need to be anodized to prevent corrosion by being immersed in specific chemical substances. Subsequently, these panels are raised and forged into fuel and oxidizer tanks using a vertical friction stir welder. Notably, 𝗤𝗂𝗃𝗲𝗃𝗃 and Vulcan Centaur rockets use 5 panels for their tanks, while Atlas V uses only 4. In this rocket assembly factory, over 1,000 workers operate various equipment ranging from machining tools to cranes. After completing the tank section, the circumferential friction stir welder installs the dome and completes the fuel compartment. The next step involves spray-on foam, 𝗖𝗄𝗃, using a high-pressure spray pipe. In this area, the tank section is sprayed with a base coating to protect it from acoustic vibrations during liftoff. 𝗖𝗄𝗃 is typically applied to Vulcan Centaur tanks to shield cryogenic fuel from excessive heat. Once the base coating and 𝗖𝗄𝗃 spray are completed, the final paint spray for the outer layer follows. Once the tanks are completed, they are moved to a temporary storage location where they will later be joined with the rocket's body. Pie-shaped sheets will be combined with domes or bulkheads for the 2 Centaur tanks. Using a combination of spot and seam welds, bulkheads and tank skin sections are integrated. As 90% of the Centaur structure's weight during launch consists of fuel and oxidizer loaded before liftoff, the tank's pressure is stabilized. All systems undergo extensive testing at the end of production, and the next step is readiness for transfer to the launch site. Rockets such as Atlas V, 𝗤𝗂𝗃𝗲𝗃𝗃 and Vulcan Centaur are transported approximately 1 mile from the factory to the Tennessee River dock. The rockets travel for 8 days to reach Cape Canaveral, or 23 days to Vandenberg Space Force, the location of ULA's RS rocket ship headquarters. Upon arrival, the rocket is transported by an abnormal load truck to its launch site. During launch, workers from the complex technical specialists and aeronautical engineers departments initiate the process with vertical integration. This process requires coordination and protection for all rocket parts to prevent failure during launch. Within the rocket launch complex, there is a launch mount or pad specifically designed for rocket launches into space. This complex also features a special platform for technical specialists and aeronautical engineers to inspect the rocket before launch. ULA successfully launched rockets 140 times in 2022, achieving a mission success rate of 100%. In addition to ULA, another renowned rocket factory is 𝗤𝗍𝗃𝗄𝐵𝐵cy Heavy Industries, located in Japan. The main rocket production facility at 𝗤𝗍𝗃𝗄𝐵𝐵cy Heavy Industries is located in Nagoya Aerospace Systems Works, Oye plant. The company has long focused on the aerospace and aeronautics industries. Some rockets produced by 𝗤𝗍𝗃𝗄𝐵𝐵cy Heavy Industries include JAXA's H-2A and M5 rockets. To create a robust rocket, 𝗤𝗍𝗃𝗄𝐵𝐵cy Heavy Industries uses 2 mm thick ISO grid, which is then cut into aluminum and titanium sheets. In the dedicated fuel tank assembly area, the rocket's tank section is integrated with other systems. The rocket engine manufacturing is carried out at the Nagoya Guidance and Propulsion System Works site. Specifically, the H-2A and H-2B rockets use the LE-7A engine designed to operate the rocket. This rocket engine combines with hydrogen and oxygen in the combustion chamber, along with high-pressure gas, achieving speeds faster than the speed of sound. The rocket also has a 2-stage combustion circulation system for extra performance if needed. Once the engine is installed, the next step involves tungsten inert gas, TG, or electron beam welding, EBW, which is a complex process. For intricate engine parts like the final machining of the nozzle skirt, it has been completed at the Oye plant. To tighten bolts, torque wrench specialists are deployed to ensure that the bolts are properly installed. In the engine assembly section, engineers use a gantry crane operated by remote control for easy movement according to instructions. If the assembly process is completed, the rocket is transported to the launch site. Typically, the rocket is transported by ship from port to port. From these ports, the rocket is sent to the launch site located in southern Japan. The ship used for transportation is a ro-ro cargo ship named 𝗤𝗂𝗄𝗏. From this port, the rocket will be transported by land to the Tanegashima Space Center for launch on Kyushu Island. For your information, Tanegashima Space Center is managed by the Japan Aerospace Exploration Agency, or JAXA, similar to NASA in the United States. At the launch site, the first section of the rocket is attached to the second section, ensuring that the segments are perfectly aligned by aeronautics engineers. After the step-by-step assembly of the rocket, solid rocket fuel boosters are installed, followed by the attachment of satellites or fairings. The process of transporting the rocket to the launch site can take up to half a day before the official launch. Before the launch of the H-2A rocket, final checks are conducted by workers to ensure that the weather is suitable and won't interfere with the rocket launch process. If the final checks are completed, the launch is initiated verbally from the control room or blockhouse. This allows all stations to track the progress of the rocket launch. Even after the rocket has been officially launched, technicians in the blockhouse continue to monitor the rocket using various systems. 2 minutes after launch, the booster section of the rocket separates from the main rocket. Once the rocket reaches geostationary orbit, the satellite payload can be released. Beyond Japan and the United States, Russia also has a company involved in rocket engine assembly called 𝗤𝘂𝗲𝗀𝗯𝗃𝗄. The company employs over 4,000 people and occupies a 90-hectare area. Workers at this expansive site develop, test, and produce rocket engines. 𝗤𝘂𝗲𝗀𝗯𝗃𝗄 has produced 107 engines for rockets operated by the renowned Russian cosmonaut Yuri Gagarin. The rocket engine assembly plant also created the advanced RD-191 engine, known for its environmental friendliness and the use of environmentally friendly fuels. The RD-191 engine operates by initially feeding gas formed in the gasifier into the turbine. There, the temperature rises to over 500 degrees Celsius and the pressure reaches 400 atmospheres. After exiting the gas turbine, the gas mixes in the combustion chamber with environmentally friendly kerosene, ignites, and is expelled through the nozzle. Remarkably, the RD-191 engine can operate in a 100% mode, a capability unmatched by any other rocket engine. The first step in rocket engine manufacturing at this plant is EDM, electrical discharge machining, where different voltages are supplied to the copper electrode, causing electrical discharge that vaporizes the metal on the workpiece. If the workpiece is not intact, its parts are joined using an automatic argon arc welding process. Most of the rocket engine manufacturing processes are not manual, so welding is also done with the assistance of machines. After these processes are completed, the next stage involves checking each detail for balance testing. During this checking stage, the workpiece is rotated at an incredible speed to determine if the torque axis aligns with the desired constructive alignment. If any deviations occur during this checking process, workers resort to conventional methods, such as using clay to create the desired balance. The clay is placed on the part believed to be unbalanced, and the workpiece is rotated until its balance reaches the desired target. The next stage involves the assembly of other engine parts or elements and a series of operations to prevent foreign particles from entering the workpiece. After the rocket engine is assembled, the testing phase begins with firing tests. This phase starts with the rocket nozzle simulating the flight cyclogram. To check the efficiency of all systems, especially thrust control, experts install cameras that will be deflected by the rudder and moved up to 2 degrees. If the engine performs as desired, it is ready to be installed to power a rocket.